Okay, so good afternoon. We have been discussing about uncertainty analysis in the previous lecture. So we will continue our discussion on uncertainty, and after that we will discuss about the planning of experiments. So uncertainty, typically we have seen that if we have some simple relations either in terms of product of the primary variables or addition of the primary variables, then how we can actually do calculate the uncertainty in the resultant quantity. There are certain equations where we can have large number of primary variables in certain systems, and there the relationship in between the resultant outcome and the primary variable can be complicated. So under these circumstances, if we have large amount of data set available and large number of variables involved, what we can do, we can utilize the finite difference approximation for estimation of the uncertainty. So we have this resultant. Here we have this resultant, which is a function of, over here say, x1. Okay, though it is depending upon other parameters x2, x3, x4, x5 as well, but what we are doing in this particular measurement, we are only say changing the value of x1. So upon changing the value of x1, whatever my resultant quantity will be there, that I have written as r of x1, x2, x3, so on up to xn. Likewise, if I slightly give deviation or perturbation in the value of x1, okay, so I have given small perturbation in the primary variable x1. Now, upon the perturbation, what will be the change in the resultant quantity? That is given by this r of x1 plus delta x comma x2, so on up to xn. If likewise I do for r2, r of x2 and then r of x2 plus delta x2. Okay, so what is delta x1 and delta x2? Delta x1 and delta x2 are the perturbations in the values of variable x1 and variable x2, and upon giving these perturbation, we are trying to check the sensitivity that how much our outcome or resultant parameter is actually changing. So this way I can calculate the value of resultant quantity for all the variables involved in this situation and for all the variables with perturbations in that particular variable. Okay. Now, if I have to calculate the del r by del x1, okay, so del r by del x1 using the finite difference method can simply be written in terms of resultant at x1 plus delta x1 minus resultant at x1 divided by delta x1. So using the Taylor series approximation, you can simply get this equation, and the order of accuracy of this equation will be of delta x1. Likewise, del r by del x2 also you can calculate, and del r by del x3, del r by del xn. In this way, what is our final uncertainty? Wr is nothing but del r by del x1 into w1 square plus del r by del x2 into w2 square plus so on up to whole power 1 by 2. Okay, so this way what we can do, we can utilize the computers. Okay, so if you have large data set available and large number of variables involved, then for complicated data set, instead of using the hand calculations, because hand calculations will be difficult, say if you have thousands or 1 lakh data points available. So under this scenario, we can utilize this type of finite difference approximation for estimation of the derivative quantities, in our uncertainty equation, and with the help of computer, we can easily determine the value of uncertainty in final measurement. Is this point clear? So the whole utility is that whatever complicated function you have, if your number of data set are less, if mathematically you are able to calculate the derivatives del r by del x1 and del r by del x2, it is easy to determine. But the major issue comes if you are finding mathematical difficulty in calculating the derivatives, or second situation is you have large quantity of a large number of measurements involved. Say you have 1000 measurements involved. So by practicing with pen and paper, it will be becoming extremely difficult and time consuming task to calculate the uncertainty. So there we can utilize computers for estimation of uncertainty using this type of finite difference approximation. Okay. Now one more important thing we have to decide in experiments. Whenever you are making the measurements, you will be getting certain data. Say one quantity you are getting 25, other 25.4, 25.7, likewise 23.2, maybe 27.8. So you can have multiple readings obtained from a single set of condition which is maintained during the experiment. Now, out of all these quantities, how to decide that which quantity is actually not a good representative of the sample? Okay, so ultimately what we do in experimental data, we try to repeat the experiment for large number of times, and after repeating the experiment for large number of time, typically we take the average value as representative of the sample. Okay, so while we are calculating the average, it may happen that in our sample some of the readings are not good representative of the particular experimental condition. These readings may have deviations from the mean value or true value sufficiently larger than the statistically accepted values. Okay, so to decide that which of the readings we are having which should not be considered for further analysis, we have one criteria which is known as Chauvenet's criteria. So what does Chauvenet's criteria does? It calculates the standard deviation of the readings we have obtained, okay, and it also calculates the deviation of each reading di, which will be equal to d bar minus, which will be equal to x bar minus xi. Is this point clear? So say if xi represent the arbitrarily any reading where I will be varying from 1 to n, then, and x bar is the sample of that mean, then mean minus xi mod of this will be giving me the deviation value for each and every reading. Out of all the deviations, if I calculate the maximum deviation and take and divide it by the standard deviation of that particular sample, so we have ratio of maximum acceptable deviation to standard deviation, and this ratio is defined depending upon the number of readings which we are considering for calculating our deviation as well as the standard deviation. Okay, so if you have 3 readings, then if the deviation divided by sigma is less than 1.38, it means all our readings are considerable. If deviation of any reading is beyond this limiting condition of 1.38, then we have to actually remove that reading, and with the remaining readings we have to do the further readings. Is this point clear? So likewise, you can see that when the number of readings are increasing, then the limit of allowable deviation has also increased. Okay. So here you can see one example. For example, this is reading number 1 where deviation di by sigma is 0.499, reading number 2 where deviation is 0.187, and likewise how many readings we are having? 10 readings. Now you can see that for 10 number of readings, what is the acceptable value of d max by sigma? It is 1.96. So you can see all these quantities are less than 1.96 and all these values are also less than 1.96. But reading number 5 is having di by sigma greater than 1.96, which is the maximum allowable limit. It means that whenever I have to consider this these sample of readings for further analysis, I have to remove this reading from the sample. And after removing this reading from the sample, with remaining 9 readings, again I will be actually performing my analysis, and there I will be again checking that if anything is going beyond the maximum limit, and then we will be proceeding further. Is this point clear? So if someone says you that you have this type of readings obtained, then how can you find out whether this which of these readings are not to be considered in analysis? That is something which we can decide from the Chauvinet's criteria. So this is the limit of Chauvinet criteria, which is presented in the graphical form, because in the previous table you can see the table is not in the continuous form. You have finite number of discrete readings only available in the table, but whenever you will be doing the actual measurements, you may have the number of readings in between these multiple readings as well. So for these conditions you can refer the graph, which is a continuous curve based on the number of readings. Okay. Now one more test is there, which is called as chi-square test, and chi-square test is typically used to test the goodness of a fit. So typically why goodness of fit is required? Say you have done some experiment and you know that from theoretical analysis some known values, like say known values under different conditions were x1, x2, so on up to xn, and the measured values were y1, y2, so on up to yn. Now if you have to estimate whether the known values and measured values are having good correlation with each other or not, that how we can test. Okay, so to test that we typically do chi-square test. So for chi-square test we calculate the chi-square value, which is given in terms of summation I varies from 1 to n, observed ith value minus expected ith value whole square divided by expected ith value. So likewise we will be calculating the value of chi-square, and this chi-square, so all these quantities are nothing but the values of chi-square, and this f is something which represents the degree of freedom. So what is degree of freedom? Degree of freedom is actually number of readings minus number of constraints. Okay, so by using this thing, number of readings minus number of constraints, you can calculate the value of f, and then for different values of chi-square, with f and chi-square value, say your f for some quantity is 8 and chi-square is 2.73. So based on this you can see that the probability of 0.95 is there. Okay, so if the number is less than this critical limit, in that case you will be considering the fit is having good correlation. So you can test this with the help of this example. For example, here I am having type of defect. So typically two types of cups are fabricated, and once the cups are fabricated, 8 different types of defects are actually quantified from a sample of 2 different cups. So in sample A, which consists of cup A, say first type of defect is present only in 1 cup. Second type of defect is present in 2 cups. Third type of defect is present in 3 cups. Likewise, fourth defect is present in 25 cups. Fifth defect is present in 10 cups. And accordingly, the number of cups having this particular type of defect for category of cup B is also given over here. Okay. Now, we have to test that whether the cups which are manufactured or fabricated using machine A and the cups which are fabricated using machine B, whether both the machines, whatever defective cups are producing, are these having the same level of defect or different level of defects. Okay, so to test this, what we will be doing, we will calculate the value of f. So f is, so how many number of defects we are having? 8 different. And what is the constraint? The constraint is only one, because we are trying to test the defect available in the cup. Okay, so 8 minus 1, that 7 is our value of f. Okay, and one more important point is, whenever we will be calculating the value of f, or we will be applying the statistical analysis, we have to also keep into mind that under each category of readings we have good representation from the sample. Okay, so typically if you see, because whenever we do apply the statistical analysis, our number of readings should be sufficiently enough. If number of readings are very less and then we try to apply the statistical analysis, then it will be giving the irrelevant outcome. For example, if you simply consider the two number of readings, and for two readings if you try to calculate mean and standard deviation, that is of irrelevance. So typically whenever we apply the statistical analysis, it is desired that number of readings for each category should be at least greater than 5. Okay, so if we see in cups which are of type A, the reading number 1 or defect number 1, 2 and 3, the corresponding quantity of defected cups are actually very less, and these are less than 5. So this does not represent the good statistical sample. So in order to make it a good statistical sample, further what we will be doing, we will club together defect 1, 2 and 3 and make it as a single category of defect combined 1, 2, 3. If we do so, we will be summing up all these values and my ultimate number will be coming out to be 6 and this number will coming out to be 14. Okay, but the number of readings in this sample will be actually decreasing from 8 to 6. Is this one clear? So that is what we have done in the next slide. So here you can see the defect of type 1, 2 and 3 is clubbed together, and this is 6 and 11, and the total number of defects now which we have is actually 6. Okay, so in this scenario, if I have to calculate the value of f, this will be coming out to be 6 minus 1, which is equal to 5. And the value of chi-square, what is the value of, how to calculate chi-square? Observed value minus expected value. Okay, so one type of cup category I will be considering as a observed value, because we have to correlate these two categories, and other I will be considering as the expected value. By using this formulation, if I calculate, the value of chi-square will be 7.145. Okay, now what you can do, you can go here and for f equal to 7 and chi-square equal to how much? 7.145. So chi-square equal to 7.145, close to here, you can calculate the corresponding value of P. Okay, and the corresponding value of P, if you test, it will be coming close to this 0.5. Okay, so ultimately the value is 0.43. Okay, so typically if the value of probability is this P value, if it is greater than 0.5, then we say that the samples are having good correlation. If it is less than that, then we will be saying that samples are not having the good correlation. Okay, so it means that cups which are fabricated from category A and category B, these are having not much correlation between the defects which we have observed. Is this point clear? So where this type of test can be useful, this type of test can be useful. For example, you have a Venturi meter, okay, and while you are doing the measurements of the flow from the Venturi meter, then the observed values you have obtained for different conditions as x1, x2, x3, x4, x5, etc. Okay, and you know that theoretically also under the given conditions that what should be the volumetric flow rate which you can obtain from the venturimeter, or say you have observed the volumetric flow rate from the rotameter in the same measurement. So flow rate obtained from rotameter is y1, y2, y3, y4, y5 likewise. So if you have to correlate whether the values obtained from rotameter and venturimeter, these are having good correlation or not, what you can do, you can apply the chi-square test. Is this point clear? Now let's talk about planning of experiments. So with this analysis, whatever briefly I have presented, we have come to know that whenever we do the experimental measurements, what are the quantities which we have to consider, what are the readings which are actually statistically logical to consider for further analysis, and what is the process by which we can eliminate some of the readings which are not statistically true representative of the sample. Okay, so after knowing all this understanding, what we have to do, we have to now slowly move towards the experimental planning. Okay, so I have already given you some idea that in case of multi-phase flow situations, because situations are very complicated and very specific to the individual physical scenario which we have considered, so majority of the time we will not be finding that standard experimental facilities are available. Okay, so majority of the times what we need to do, we need to develop our own experimental facility. So once we have to develop the experimental facility, we should also know that how to plan for the experiment. Okay, so what are the steps involved in planning of an experimental facility, that I will be explaining to you. Okay, so first I will give you the general brief about the steps, and then we will try to see all these steps with the help of an example. So you just tell me, if you have to plan some experiment, can you just answer me what are the things you need to do? In a general way, I am not asking about any related to any specific experiment, but in general, if you have to plan an experiment, so what should be the initial strategy? How you should start? Boundary conditions, okay. So
what goal, what we have to observe?
yes. So first thing is our goal and objective should be clear to us. Okay. And once our goal and objective is clear to us, then we have to list down that what are the primary variables that shall be investigated. For example, if your simple objective is that you have to define and you have to design an experimental facility for measuring the pressure drop inside a pipeline. Okay, so what type of measurements you need to do? So this is your objective. Now for measuring the pressure drop, what you need to do? You need to decide the primary variable. So for pressure drop inside a pipe, you know the primary variable can be diameter of the pipeline, it can be the length of the pipeline, it can be roughness of the pipeline, it will be either velocity of flow or say flow rate within the pipe. Okay, then what else?
Change in cross section.
If there is any cross section change, so that already we have accounted in the diameter. If say in a straight pipe, we have to determine it. So that is our objective. What else?
Type of fluid.
We have to decide for which fluid or what are the fluid properties, because ultimately we have to freeze what type of fluids, whether I will be doing it for air or I will be doing it for water. What else?
Orientation of pipe.
Orientation of pipe. What else?
Turbulent flow, air laminar flow.
Okay, so for checking that, what we need to do? Reynolds number. But Reynolds number will be coming as a dependent quantity. Okay, because right now I am just talking about the primary variables. What else?
Pumping power.
Pumping power. For deciding the pump, what type of pump you have to use, because experimentally you are trying to measure the pressure, so you also need pressure gauge or pressure transducer for measuring the pressure. Okay, so pressure also you need to measure. So all these are the quantities which are nothing but the primary variables which you need to record. Okay, once you have decided these primary variables, then you have to decide what control must be exerted on the experiment. What is the meaning of this? So whenever you are using this experimental facility, you cannot randomly go and then say you have taken a 1 kilometer long pipeline. It is not possible. So you have to decide what should be the length of the pipeline. Then it is also not possible that you can take excessively high value of flow rate. Of course, your flow rate and pump capacity should meet. Okay. Then you have to decide which type of fluid you have to use. It may happen that you are considering that you want to pump highly viscous fluid or say heavy density fluid like mercury in the pipe. It may not be safe. Okay, and ultimately you have to freeze your Reynolds number, whether you want to operate in the laminar regime or turbulent regime. So for freezing that Reynolds number, you have to suitably also select the fluid properties. Okay, availability of the fluid. So all these controls, whatever range of these variables you want to operate, that range we will be actually freezing, because Reynolds number could be 1 million, it could be as small as 2000, it could be as small as 20. So you have to take appropriate decision or appropriate call that under what conditions I need to control this. Then other controlling conditions, for example, what are the ambient conditions? Whether you want to do this under atmospheric temperature condition or you want to operate the pipeline at high temperature conditions. So all these things we have to decide. Okay. After deciding the control, then range of primary variables, of course, that I have already defined under controls as well. And then after that we have to decide that how many data points should be taken. So if your experiment is simple and it is not involving much cost, like pressure drop measurement inside a pipe, there we may not be much concerned about the number of readings, because easily we will be just switching on the setup and we can take as many readings as possible. But the experiments which involve significant amount of cost, which involve significant amount of time and resources, there you have to judicially decide that how many number of data points should be sufficient enough so that our experimental reading is also correct. At the same point of time, our resources are also not being wasted. Okay, for example, if you have to do the experiment of boiling inside a nuclear reactor, okay, so ultimately it is not very easy to just do the experiment and then obtain the reading and then decide, no, this experiment is wrong, let me do it again. Okay, so you have to do a proper planning for that. So whatever number of readings you have to taken or number of data points you have to taken, that also you should be deciding a priori in order to have a good sampling of data. Okay, ultimately what is the next point? What accuracy of instrument is required? Why this point is important? Because we have seen that through our uncertainty analysis, the accuracy of the instrument decides the uncertainty of primary measured quantity. and ultimately that gets translated to the resultant quantity which we are actually obtaining. So if I am putting huge restriction, so ultimately you may think of that you will be choosing the best accurate instrument which is having the least uncertainty. But it may happen that the best possible instrument, say there is one ultrasonic flow meter which is having accuracy in the range of, or uncertainty in the range of plus minus 0.01% of full scale. There is a turbine flow meter which is having accuracy in the range of 0.1% of full scale. There is one another flow meter, say it's a rotameter, which is having accuracy in the range of plus minus 1% of the full scale. Now, to your mind, it may happen that you will be choosing which one with accuracy of 0.01%. But it may so happen that ultimately this equipment is very precise, but the corresponding other measurement quantity or other equipment is not having that much good uncertainty, and this variable is contributing least on the uncertainty of the final outcome. So you have actually wasted your resources over here. Okay, so it cannot happen that your entire pressure drop measurement setup is say of 20,000, and in that one flow meter you have put which is of the cost of 25 lakhs. So that will not be justifying the requirement of the whole measurement. So ultimately you have to make a compromise in between the desired accuracy requirement as well as the cost involved with the system. Is this one clear? So based on that you have to make judicial call in order to decide the instrument. After that you have to also understand that whether dynamic measurement is involved or not. So for example, if you consider the pressure drop through a pipe, if your interest is only to measure the pressure drop under the steady conditions, then experiment will be keep on running for long, and after it has become steady, at that time you can simply take the reading. Okay, but there can be certain scenarios, say if your interest is you have to also determine the oscillations or fluctuations in the pressure which are happening during the developing flow condition. So under this scenario what will happen? Whenever you switch on the pump, flow will just start coming, and say in 5 seconds or 10 seconds it is becoming fully developed, and your interest is that once you switched on the pump, from that duration to 10 seconds, whatever is the variation of pressure, that also you want to capture. So now your measurement type has become, instead of static, measurement type has become dynamic, because at each and every time you have to record the value of pressure. So if at each and every time you have to record the value of pressure, then your Bourdon tube pressure gauge will not work, because ultimately its reading will keep on deflecting and it will be only representing a steady value once all the physical conditions are maintained. So in that scenario, instead of the Bourdon tube pressure gauge, you may have to use a pressure transducer ultimately, and the frequency response of the pressure transducer, whatever you are considering, that should be faster in comparison to the required sampling rate of the data. The simple example is, for example, if your requirement is from 0 to 15 seconds, at every 1 second you want to record the data. What is the value of pressure after 1 second, 2 seconds, 3 seconds? Then if the response time of the transducer is 5 seconds, what ultimately it will be doing? For all the values of 1, 2, 3, 4, 5, it will be giving a single value. Okay. So your response time of the sensor should be so selected such that it is less in comparison to the requirement of the dynamic measurement. Is this one clear? So for dynamic measurements we have to go for particularly the response time of the transducer will be important, and response time of transducer should be less in comparison to the requirement of the dynamic measurement. Is this one clear? Then next is whatever the instruments you have chosen, are these commercially available or they must be constructed especially for the particular experiment. So always whenever you are designing experiment, your effort should be that all the things should be try to use the instruments which are already available in the market. Okay, because if say you have selected some instrument which is not available and first you have to fabricate the instrument and then you can do the measurement, then ultimately it will be cost involved and time involved. But there are certain scenarios for which actually you cannot avoid and then you have to construct the equipment as well. Okay. What are the safety precautions? So this is very important thing. Okay, so safety, while we are deciding the experiment, we have to also keep into mind the safety. Say you have taken certain pressure conditions which are excessively high, and corresponding to that there are chances that pipe can burst, so it can be harmful to the user who is performing the experiment. Okay, so that's why safety considerations are also need to be accounted for. And then of course finally, and the most important one is the financial resources. Okay, so say if in your design practicum project you have 30,000 to design some prototype and you choose a single sensor of 50,000 cost, then ultimately you are not able to do that. So financial constraint also you have to keep in mind. And of course, whenever the dynamic measurements are involved, then we have to record the data. So for recording the data, we have to also choose certain methods. If data recording is only the steady measurement using pressure gauges or this, then it can be done manually on data sheets. So proper data sheets should be made for that. But if dynamic measurements are involved, then you have to use the appropriate data acquisition systems as well as the computer for storing the data. Okay. And what provisions has been made? So that is already considered. And this is the generalized experimental procedure. So all the points which I have explained, how in flow chart simultaneously these points are actually seen and we fluctuate or we consecutively keep on moving between the consecutive points, that is actually explained. So you can go through this. I will be providing you these slides. Then this is the general data acquisition system, general layout of the data acquisition system. So typically physical property is sensed by the transducer and that is through input circuit. It is transformed in the form of a signal and that signal is then transmitted and processed to either display the reading or store that reading in computer, and ultimately that reading then can be either just used for post processing or it can be further used to perform some specific task in the experiment. Okay, for example, if you have a simple system where your interest is that you want to maintain the temperature of water at 50 degrees Celsius. So if you are using a thermocouple over here, so this thermocouple will be giving you the actual value of temperature. If that value of temperature is less than 50 degrees, say 40 degrees Celsius, then your heater will here switch down. If the value of measured temperature is say 51 degrees Celsius, which is greater than 50 degrees Celsius set value, then you have to switch off the heater. So in certain scenarios, whatever the value we are obtaining from the transducer, that can be utilized for other function. For example, over here the reading of the thermocouple is actually utilized to either switch on or switch off the heater. Okay, in certain cases it may be just a reading for obtaining some output variable during the analysis of the experiment. Okay, this is a multi-channel data acquisition system, and of course whenever we are talking about the multi-channel data acquisition system, then we have to consider the frequency response also. So now all the points which I have explained you earlier, these are given in point form, in systematic form, and with the help of this general table, you can actually prepare your experimental plan while you are going to design the experimental facility. So for example, the first item in your sheet will be overall objective of the experiment, and that overall objective will be depending upon the, either if you are working in a R&D organization, then it may be dependent upon the requirement of the management, or if you are trying to working in some consulting firm where you have to do it for some external customers, then depending upon the requirement of the customer you have to decide the objective. And then if anything specific is need to done to refine the objectives, that you will be deciding, and what are the other factors which can actually control your experiment. Okay, so that has to be decided in the starting itself, and then we have to identify the list of specific results that are need to be included, including the ranges of all the primary variables, accuracy of the instruments, and whatever is the desired uncertainty range. And after that we have to identify the number of readings, sample representations, what will be the methods and procedures for performing the experiments, parameters which are to be calculated based on the primary measurement quantities, and then expected range of measured quantities. So outcome should be in what range. And this is apparatus design, then sample calculations, and decision on measurement method. So after you have done the what comes under this decision on measurement method? I have already explained this in the last lecture. So for example, if you have for measurement of power, either you can do it by using I square into R or E into I. Okay, so you have multiple options available. Then through the uncertainty analysis which has been performed in step number 12, you have to decide that which type of method you will be carrying forward for further analysis. Okay, and ultimately with the once you have frozen your method, then you can calculate the final uncertainties. Once final uncertainties are calculated, then if you feel or if you find that uncertainties are not in the expected range, then of course at certain level you may have to redesign or re-look into the experimental setup. So that part we will be doing in the 15th step. So you can see all these steps, whatever I have listed over here, one has to do before planning the, performing the actual experiments or before designing the actual experimental setup. Okay, so all this analysis is to be performed before the setup, and whatever is to be done after the setup, that is almost clear in step number 11 and 12. So it means whenever you plan an experiment, it does not happen that let us first randomly design something, obtain the measurement, and then whenever you started obtaining the output, then you see, oh, this variable is missing or this should be done in that way. So that part is actually not preferred, because ultimately that will be wasting your time and it will be involving more resources and more cost. So that's why always your experimental planning should be done properly a priori, and all the factors which will be controlling the experiment, these are should be decided before. Okay, for example, you can see whenever we are developing the small scale experimental setups, where this type of analysis, if not done properly, then also it is not going to cause major issues. But say if the facilities like nuclear reactor or facilities like spaceships, or say different missions of the space organizations are being planned, which will be taking say total project duration of 4 years or 5 years. If there this type of proper planning is not done, it may so happen that after 3 or 4 years you may come to know that whatever this thing you are developing, this thing is not going to work. Of course there also these things happens, but this should happen at very small scale. It should not have any type of random initial consideration, which is ultimately going to cost you the entire time and resources involved in that big project. Okay, so that's why this type of analysis, and whether you are going to develop a small experimental facility for measuring the pressure drop, or you are going to build something for a big say space experiment, everywhere this type of general analysis need to be performed. Okay. So let's try to understand all these procedures with the help of one experiment where our objective is to determine the forced convection measurements for a new refrigerant. Okay, so what is the meaning of this forced convection measurement for a new refrigerant? Meaning is someone in the laboratory have designed, say, with the help of some chemical composition or something, some material scientist has come up with a new special type of refrigerant, and now the interest is the scientist wants to test what are the heat transfer characteristics of this particular refrigerant under the forced convection conditions. Okay, so what you need to do? You need to, what do you mean by first heat transfer characteristics under forced convection conditions? Heat transfer conditions under forced convection conditions.
Let's calculate the new.
Yes, so mostly whenever forced convection is involved and our interest is to calculate the heat transfer characteristics, our interest will be in identifying H, which is known as convective heat transfer coefficient. Okay, now can you tell me the name of device, any instrument or any device which is which can give me the value of heat transfer coefficient? Like for thermal conductivity, for density, for viscosity, we are having many equipment or devices available with the help of which we can actually measure the value of these properties, including specific heat, etc. Is there any equipment or instrument available which can give me the value of heat transfer coefficient, like I have placed it somewhere and it has given me the, or say I have loaded certain sample in it and it has given me the value of heat transfer coefficient? Is there any equipment available? So heat transfer coefficient is something which is actually specific to the physical configuration which we are considering. So that's why as such we do not have any standard equipment available for that. Okay. So now whenever we will be using the refrigerant, so if we are specifically talking about the refrigerant typically we will be using either inside a home refrigerator or in an air conditioning unit. Okay, and whenever we will be using home refrigerator or air conditioning unit, typically these units involve copper or aluminium tubes, and inside these copper or aluminium tubes our refrigerant actually moves. So ultimately the physical situation which we need to consider is that we have to study the internal forced convection. Is this point clear? All are clear with this idea? So we have to study internal forced convection. Okay, so it means whatever the setup we have to develop, we have to keep in mind that we are developing it for internal forced convection. Okay, now let us try to see what are the constraints which are given over here. So fluid properties for saturated liquid condition. So normally the experiment which we need to perform in the saturated regime, and at saturated liquid conditions the properties are to be varied from 0 degree Celsius to 40 degree Celsius. So our operating range of temperature is 0 to 40 degree Celsius. Then density of refrigerant is 1200 kg per meter cube. Its saturation pressure is 300 to 1000 kilopascals for the given range. Dynamic viscosity is closely can be approximated because pressure and temperatures are different. So of course at different pressures and temperature this will be different, but over here it is, its value is given close to 3 into 10 to power minus 4 kg per meter second. Thermal conductivity is also given, specific heat is given, Prandtl number is given to be 5.6, and the desired range of Reynolds number in which we need to operate is from 20,000 to 1,50,000. Okay, and fluid liquid temperature is same as given above, 0 to 40 degrees Celsius, and flow geometry. So we have to perform the experiment in smooth circular tube, and the tube diameter should be ranging from 2 to 35 millimeters. Is this one clear? So tube diameter has to be within 2 to 35 millimeter, and length of the tube should be sufficient for developed flow conditions. So we have to use a straight length, and that length should be so selected that it is having the sufficiently developed flow conditions. And what is the temperature difference between the tube and fluid? So we have to operate in such a range so that the temperature difference between the tube and fluid is 5 to 15 degrees Celsius. And heat fluxes, so range of heat fluxes will be as per the whatever we are obtaining during the experiment. Similarly, flow rate will be also. So for flow rate, what is the constraint? Reynolds number is the constraint, and based on this expected flow rate we have to use. Why they have not given the flow rate value? Because till now we have not frozen anything. Tube diameter is also in the range, so that's why flow rate is difficult to determine unless or until tube diameter is actually known. So that's why this also we have to decide. And desired uncertainty in determination of, so whatever range of uncertainty we have to maintain is how good one can get. So with this physical situation given, we have to now define or design the experimental facility for measurement of heat transfer coefficient. So can you first tell me, because whenever you will be going to this analysis or deciding different equipment, before that you should have a general idea of the general layout of experimental facility, how it should look like. So can you tell me how our experimental facility should be? One point is very clear, that there should be a straight tube. Okay, there should be a straight tube through which refrigerant will be flowing, and we have to determine heat transfer coefficient. Is this one clear? So first point is, in my experimental facility should involve a straight tube, and other point is, this straight tube, the length of the straight tube should be in such a way so that for the measurement flow is developed. So say if at this point flow is entering, then I will be having some developing region, and then I will be having some developed region. Okay, is this one clear? Now I have to study the heat transfer between the tube surface and the refrigerant. Okay, so if I have to study the heat transfer between tube surface and refrigerant, then there should be temperature difference between the tube surface and the refrigerant. So in order to ensure the temperature difference, what we need to do? We need to heat the tube. Okay, so what I will be doing, I will be putting some heater coil on this tube. So this is my heated section of the tube. Is this point clear? Now you have to understand that it is given in the experiment that heat transfer is to be studied only in the developed region. That's why I have not included the heated portion in the developing section. All are clear with this point? So heated portion is in the developing region only. So what it will does, heated section will heat the tube, and refrigerant will be coming at some inlet temperature which will be less than the wall temperature of the heater, and ultimately heat transfer will be taking place from tube to the refrigerant. Is this one clear? Now, whenever you have this type of configuration, you have to continuously allow the refrigerant to flow through the tube. So what you need? You need a pipeline which is connected to a pump. So here you will be having some pump, and of course this pump will be collecting the refrigerant from some reservoir or tank. Okay. Now it may happen that to ensure the steady condition, you need to allow the refrigerant to flow through this tube for say 10 minutes or 15 minutes. Okay, because ultimately heat transfer coefficient, in order to allow that, we have to maintain the steady condition. So for obtaining steady condition, time will be taken. So if experiment is to be repeated for say 10 minutes or 15 minutes, then ultimately what will happen? If you do not return this refrigerant to the tank with its original state, then ultimately you need large quantity of refrigerant, and whatever refrigerant is coming out of this will be wasted. Okay, so ultimately what we need to do now? We need to recirculate this. So for recirculating the refrigerant, what I need to do? And again I have to bring this to the original state. So from here to here, in the heated section, its outlet temperature will be increasing, but my interest is whatever is the refrigerant temperature within the tank, it should return to the same temperature condition. So for doing that, I have to, whatever the refrigerant is coming out, I have to pass it through some heat exchanger. So depending upon the state, if it is has become vapor, then my heat exchanger will be acting as a condenser. If it is remaining in the same liquid state, then it will be simply a normal single phase heat exchanger. Okay, so what I have to do over here, I have to use one heat exchanger. Okay, and this heat exchanger then will be bringing it to the original state. Is this one clear? After that, whenever this refrigerant is moving, I have to measure its flow rate, because to calculate Reynolds number I have to measure its flow rate. So I have to put somewhere over here a flow meter. Then ultimately the pressure of the tube need to be defined. So I need to do measurement of pressure of the tube. Okay, what I need to do measure? I need to measure the temperature. So for measuring temperature, I need to insert the thermocouple within the tube first to measure the temperature of the refrigerant, and other than that, at the wall of the tube to measure the temperature of the tube wall. Is this one clear? Other than that, here also I need to put thermocouples at multiple locations. Then other than this, what I need to do? I also need to measure the heat input to the tube, which we are providing through this heated coil. For measuring that heat input, what I need to do? Heat input is nothing but electric power. So for measuring electric power, I need to use voltmeter and ammeter. Okay, so ultimately I need to measure the voltage and the current. Then I will not be doing experiment only at the single heat flux condition. I may have to repeat this experiment for multiple input powers. So if I have to repeat this experiment for multiple input power, then whatever the voltage and current I am supplying, I may have to supply it with the help of some variable power supply, okay, which will be varying the amount of power which we are giving to this wire. All are clear at this point? So now you can see that we have not exactly identified what type of flow meter, what type of thermocouple, what type of pressure measurement device, or what type of voltmeter ammeter we will be choosing. But what we have identified in this first trial, based on the given physical situation and our requirements, we have just planned the basic layout of the experimental setup which we need to develop. Is this point clear or not? Okay. So for this small, see the quantity is very small. Only we need to measure heat transfer coefficient. And for measuring this single quantity, we have to develop this much big experimental facility which is involving so large number of primary measurements. However, till this stage also we have not yet decided that how many thermocouples we will be inserting on the wall. Okay, all these things are still under consideration and we need to decide upon. Okay, so please try to re-look into this basic layout of the experimental setup which I have specified over here, and if you feel that any of the components are missing which I have not considered and are to be accounted for, then let me know. Okay, and the specific calculations about the selection of different measurement devices and the number of measurements I will be discussing in the next lecture.